Hi guys, this clip is a bit longer than some of the others, but I think you'll enjoy it. It's about the working properties or mechanical properties, they're both connected. And Jake, what was the other one?
Physical properties.
The physical properties, and we've got some little tests and things we're going to show you. Hope you really enjoy it. Bye.
So Dad, if concrete's so tough and resilient, why does it crack and break?
Right, well, as you can see in all these properties we can see on this piece of paper, okay, we've written up, not all these properties can actually be included in one material. So even concrete, as you can see, has its limitations. And although that took a lot of shock, a lot of force, it still breaks under certain degrees of impact. Although it did take a lot, didn't it? And you are very strong, of course, Jake, aren't you? Are you very strong, Jake?
Yeah. So let's start off with biodegradability.
Biodegradability, yes, that's a complex word in some cases. That's when a material actually degrades and falls apart, rots, I suppose, over a period of time. And some products are designed to rot quicker than others, but some they have to be protected, like some metals have to be painted or galvanised or electroplated. But you know, leather lasts for a long time, but it does degrade if you put it in the ground. And ultraviolet light from the sun damages most products. But some plastics are designed to degrade over time or rot, so they don't cause damage to the environment. And actually I think that's the way everything should be going. Things should only have a small lifespan if they are likely to be in some way disposed into the ground. Woods don't rot that easily, they're not all of them. Some are actually very resilient. That's a key from a piano, that's made from ebony.
Wow, it looks like it's just painted.
It looks like a plastic, but very dense, heavy material. But stainless steel doesn't biodegrade, but other steels do. They have to be coated. Copper doesn't biodegrade, but steel tends to. But biodegradability normally relates to fabrics and foods, some plastics. Yes, Jake?
So why do you see copper sometimes turning green?
It's just the way it oxidises, the way it actually forms its own sort of coating on it. It does go green, you're right. Good, yes. Okay, next.
So what about electrical conductivity?
Well, it's normally a metal. That's pretty evident in most things. So brass, lead, certainly steel, copper and aluminium. Gold is one of the best ones. Titanium's excellent as well. But they're normally metallic in some way. And if they conduct electricity pretty well, they 100% they conduct also heat very well. But it does depend on the type of metal in most cases. Some plastics, modern plastics, can actually conduct electricity, and they're the sort of smart materials that we discussed in perhaps an earlier clip. But yes, does that help?
Yeah. What's magnetic?
Well, magnetic is any material that attracts iron in some way. So there's the magnet. So if I put the magnet on certain materials like lead, has no iron in it, so it doesn't conduct. Brass, no good. That's got some iron in it, or steel, which contains same. Aluminium doesn't. Steel does. That must be a steel
what about
spring steel?
This massive
that's,
bolt.
It does attract it. That's got steel or iron in it. So anything that is steel based has iron in it. Glass is not magnetic because it's not a metal. Steel on there does, but not the brass. Ball bearings do.
Wow.
Copper on that coil there, on the clock. Oh, that's the clock I broke up. Not on copper, not on aluminium. On steel it will. Steel it will. Stainless steel, a little bit, yeah. Stainless steel.
Does it? Is it depending on the nickel content?
Yeah, it does actually matter quite a lot. Actually, yes. Oh, that's an Now I thought that was an aluminium, but there seems to be some sort of steel there. It's the steel on the top. There's combined material. That's a steel-based material. Probably a nickel. And that's an aluminium. It won't pick up that. Isn't that interesting? So,
yeah.
Not plastic, of course. It's not magnetic. A speaker is. And that speaker in the actual handheld phone there, you know those phones you use around the house, cheap ones. There's the magnet in the back of the speaker. Okay, does that help things? Stainless steel? Yeah, it does in that case, yes.
Wait, so would this drill bit have like titanium in it or something?
No, some do have tips on it, and it can be tungsten or titanium. Some even have diamond tips, make them cut through.
So is tungsten or titanium magnetic?
Tungsten is titanium. No, tungsten, I'm not sure. Titanium is. It's a good question. Some research there for the viewers, maybe.
Wow.
Yeah.
So what's absorbency?
Absorbency is anything that can actually take in a fluid, or I suppose water in some ways. So I've lost my sponge. But a sponge would be a good example. And most fabrics, not rubbers, but leather takes in water, doesn't it? Absorb water. Although it can be made quite porous by putting waxes on it and things. Rubbers aren't porous.
What about our t-shirt?
T-shirts, so cotton, wool.
What
not
about...
really nylons. Nylons don't take in water. They repel it. Well, this carbon fibre matting will, but it's not mixed with the resin. But when it's mixed with the resin, very, very impervious to water. Okay, plastics don't allow water to go through. So it's those that absorb water. That's a porous or an absorbent material.
When they make PVA, do they add water, or does the PVA attract water?
PVA is polyvinyl acetate. It's mixed with water, but it's basically polymerized. It's a polymer-based glue. So yeah, they add water to it some way. Chemical reaction when it dries. Clever stuff, PVA. Okay,
Dad, I know bolts have to take a lot of torsion, so can we test that?
Torsion, yes. Torsion is all about twisting force and the resistance to be able to be twisted. So we'll do a load of tests now on various materials. So cool. I thought we will do it on lead.
Okay.
That's a metal, obviously. Aluminium, copper. This is a carbon steel, for tool steel for hacksaw blade. That's a polypropylene, I think, or polyethylene. That's mild steel. A bit of hardboard, which is a wood. We'll use a bit of acrylic.
Cool.
Yeah. Bit of butadiene. I need to get that right. That's from an inner tube on a tyre, on some cars. Bit of Velcro, which is nylon based.
Yeah.
Glass.
Well, that'll be interesting.
It will be actually, won't it? Yeah. Some brass handle. That's the only bit of brass I can find. But I've tried to make sure the thickness is similar to all of them, and that's important. Although the shape of this actually will help it not to be twisted. But you know, we'll get an idea. And a good old stainless steel.
Yeah.
I couldn't even cut it, so I'm going to have to just go with it, I'm afraid. Maybe even a bit of mixed material with copper wire and mains electric wire. A bit of leather again. Is that from your shoes, Jake?
No.
Are you sure?
Yeah.
Trendsetter, you. Polybutylene. I think that's a more rubberized polybutylene. Expanded polystyrene there. And I think even a nylon fabric that might bend. And I might get, just stay there a minute, I might get, from the bin, some high density styrene, polystyrene.
Okay.
Plastic base, which is obviously an oil based product. Okay, so what we're going to do, I'm going to put them in the vise here. So I'll show you the vise. And I'm literally going to try and do it as evenly as I can, so it's a fair test. And I'm just going to twist it that way. Okay? Yeah. So we'll do the test now. So
this is hardboard.
There we go. And we're going to twist it.
Oh.
And it also sheared, didn't it? But you can't twist it. It's rubbish in twisting. Okay, next.
Lead.
Okay, lead. Pretty good, actually.
Wow.
Soft, but it can twist. This is a butylene rubber.
Or bicycle energy.
Yeah.
Oh,
not very resistant, but it can take it can't take any torsion really, can it? But it's a very resilient.
Yeah.
Certainly can twist. Okay. Try to move the lever up. I don't want to try and act like a shearing force, a twisting force. Here we go. And that's aluminium. Pretty good.
Yeah.
But not very resistant to torsion at all, twisting force. Quite soft, isn't it?
Mm-hmm.
High density styrene. Oh,
wow.
No, it failed. Yeah,
yeah, it just breaks into loads of pieces.
Not good in torsion. Acrylic. Oh,
wow.
Yeah, should have wore glasses for that one.
Yeah.
It's tool steel, hacksaw blade. Watch your eyes, Jake. It's pretty good. Yeah, for the thinness, it's pretty good actually.
Yeah.
Because it's very thin. Okay, that's tool steel, high carbon steel. Pretty good. What do you think this is?
The polyvinyl chloride?
Yeah, polyvinyl chloride, PVC. That's, oh no, it does, it's failed, but I can see it was actually pretty tough. So in torsion, it's not bad actually.
Yeah.
Better than a styrene.
Mm-hmm.
Yeah. Yeah, but it does fail, but yeah.
Yeah. And now the steel.
I can
Looks
hardly
like
twist
you're
it.
struggling a bit.
I know it's it's a little bit bigger than the rest, so it's not a completely fair test, but no, that's...
Is that why they make bolts out of it?
Yeah, that's so far that's toughie, because it can actually twist. It's got some elasticity in that. This is copper. It's pretty tough actually.
Even though it's generally known as like quite soft.
Yeah, it can take that twisting force though, so it has some resilience.
Wow.
The metals tend to be stronger, don't they? You can tell. This is not a very good test because it is, although it's quite thin, it's got that sort of shape to it, so it helps it resist. But this is brass, and it's pretty good. But not a brilliant test comparison, but
Yeah.
best we've got at the moment. Yeah, there you go. Right there. This is glass. It's a mirror glass. We've got safety glasses on. I wouldn't do this at home, guys. I know it's gonna happen. Let's see. Yeah.
Oh, it didn't go into a million
No,
pieces.
it's too
though.
brittle. It won't take any torsion really. So this is a nylon, bit of Velcro. I'm going to shove it in there so it's similar thickness. Now this, well, I think we all know what's going to happen here.
Yeah, this is slightly thicker than the...
Well, no, look, I can compress it easily. So I'm just going to... It's not...
So it's flexible.
Very flexible, very flexible. And actually I can't break it easily. But it's because it's so flexible, it can't really take torsion, if you like.
Yeah.
Polystyrene, I've got to be careful not to crush it because that will weaken it itself. Don't need a spanner, but I know what will happen. Yeah.
Yeah.
Well, this isn't exactly fair. This is stainless steel, but I can see straight away this is a very resistant material to twisting force, and I wouldn't be able to twist that and break that very easily. And I'm putting a lot of pressure on. So stainless steel, yeah, that's a good one.
So stronger than steel.
Yeah, stainless steel, and it would be stronger than gold, which is very soft, and silver, but not titanium, and not platinum, and probably not certain carbon fibres when they're mixed. There's a steel, and this is why they use steel for these purposes, because the properties are so perfect for things that have to go in enormous amounts of torsion. You have to resist torsional force. Does that help, Jake? It's quite a good little overall test, isn't it?
Mm-hmm.
Bit crude, but there you go. That's what we can do.
Yeah.
And lastly, leather. Well, leather, because it's so flexible, it can take twisting forces, but it can't resist them. But I bet you I could really twist that with a spanner. Quite resistant. Leather is a remarkably strong material in all sorts of areas, and that's why it's been used over thousands of years, millions of years, to shelter and protect people from the weathers and so forth. But you can get man-made nylon-based leather type material now, can't you? Right, any questions, Jake? Do you like that? It was on torsion.
Yeah. Can we test that bolt?
I haven't got the strength. I just wouldn't. I suppose we could mount this in the vise, put another bolt on it. I could do with a smaller bolt, but
Oh yeah.
yeah, that's a bolt from a lorry actually. But there you go. And today Jake twists some metal as a torsion test. So Jake, you had a question.
Yeah. What's this long thingy?
Oh, that's a fishing rod. That's your brother's fishing rod.
Wow.
Yeah, and that's carbon fibre. Look, and that is quite a interesting piece of technology. And this is very, very light, just a few ounces almost, and that extends long, very long.
Wow.
Very, very clever bit of technology. And that is this matted or glued with a resin. All right. Does that help? So
yeah.
That's an enhanced material, and that's why all these clips are really quite useful. You can see why, if they look at the materials and combine them with certain properties in terms of how they're going to be used, they can probably get a really good product. So mixing nylons with other types of materials can make a product really quite resilient and last a long time. So the properties do matter, and the mechanical properties or working properties and the physical properties together really make a difference, like this spring.
Yeah.
It's designed to take certain loads and work in certain conditions, but of course everything has its limitations. So if I overstretch it, it's gone past its design point, if you like, its yield point, and it's called technically. And we'll touch on that a little bit later when we look at stress over strain.
Wow.
Is that all right, Jay?
Yeah.
Okay. Okay, so I thought we'd do a quick summary of this clip and some of the other clips. So, and this is what, Jake? What am I testing?
It looks like some brass wire.
Yeah, so we're going to see what happens when we bend it and at what point it won't go back to where it used to be. So there. That's its yield point. It won't go back now. I have to bend it back. Can you see?
I saw you bent it a little bit more than it would have.
Now at that stage there, it's in its sort of plastic state, and then after a while it'll actually snap at some point.
Or bend.
All right,
in this
or
case.
just bend, but it will eventually snap. Okay. Anyway, that's a little bit about elasticity. This is spring steel, so you can still pull it and it's still elastic, and then after a while it'll go past its yield point and then I'll actually stretch it. There.
Ah.
Yeah, it won't go back now.
So will that snap?
It will if I keep on pushing, but I haven't got the strength, but it will actually snap, and that's where the fracture point occurs. But there, everything has its limitations. So let's do a bit more summary on this. We've done some twisting, torsional tests on lead and aluminium and copper and fabric, and we did a shear test, cutting test on a golf ball, and we've been looking at a range of materials. Jake, yes?
So why have we got these drill bits here?
Well, I was talking about tool steel and how they add carbon to it to make it harder at the tip, and they can put even diamonds on it to make the property of the actual product even better. So products often have combined materials. They wind wire together to get steel rope, if you like, from bicycle.
Cool.
They magnetise iron. We use special materials like butylene to make elastomers, elastic rubbers. Yes.
When
Jake?
you said magnetise iron, what do you mean?
Well, any magnet has to contain iron, but it has to be an iron to be able to be magnetised. We looked at opaque, translucent, didn't we? And transparent, those that you can see through. We looked at different types of polymers and how durable they are, how tough they are. We looked at how tough woods are, and we looked at bending strength, so that you can bend, okay, without it changing shape forever, but you can bend it to a limit. Okay, that's bending strength. And we looked at a mixture of properties, like in this tennis racket. This is made from carbon fibre, and has a mixture of properties within carbon fibre, and there's the matting there. Okay, so this clip's really about the properties of materials, and it talks about the mechanical properties and the physical properties, and we'll go through them in the clip a bit later. Hope you enjoy this clip, by the way, guys, some fun bits as well.
Cool.
And today we're going to be trying to make some sense of this graph we've done on another worksheet for Shedhacks, and we're looking at stress and strain and elasticity. That's the word. We're trying to make some sense, as I say, of what stress and strain are in terms of the graph we plotted there. And I suppose the key word in this topic here is the top one there, is the bending strength and the resistance to bending without permanent damage. That means it's staying permanently broken. And in relation to that, I've got a little photo there of an aircraft being lifted, and it can show the steel ropes from the crane lifting up that probably about 3 or 4 tons, maybe more, of an aircraft, possibly more with the engine. I'm not exactly sure on the weight, but those steel cables there would have been carefully designed for that crane to take all sorts of loads, probably up to 10 tons. And of course the testing would all have related to perhaps a graph like this they may have done on a test on the actual steel cable itself at some point. Anyway, moving on, because I don't want to bore you. We've done a little setup here, and we've got a number of materials of the same size, same length, and the same cross section roughly, as best we can. And we're going to just put 1 kilogram weight on them and just measure roughly how much they're deflecting. And deflecting means, in a sense, how much they're bending at that point they're gripped. So we've got plywood, okay, we've got acrylic, we've got spring steel, styrene, balsa wood, some painted aluminium, some mild steel there, and a piece of Douglas fir. That's slightly thicker, that, but it's the best we can do. Okay then, Jake, let's go with the 1 kilogram weight.
So we're going to measure how much it bends.
Try and put the weight on the end as much as you can so it's even on each one.
There it's about 50.
50 mil deflection.
Well,
Yeah, on there, same place, please. There,
it's about 65
millimeters. Spring steel, right on the end there, Jake, please. So it's an even.
It's about... Oh, wait, it came off. It's about 25.
25 mil, put the whole weight on, of course.
Oh.
Oh. Okay, so the styrene
Yeah, it won't even take it.
won't take any weight, so it's a fail.
Then that...
Oh, that's broken. That's broken. It won't bend
So
as
it's
much.
fail then.
Balsa wood is quite strong, but obviously in this test it has a limit.
The aluminium... It's about 50.
50 mil. I know it's being painted, but that's aluminium. 50 mil. Is that only 50? 50 plus. 55,
Yeah.
I think that was about. Steel, mild
About
steel.
40.
42, 43, yeah, millimeters. Okay.
And then the
Oh,
pine...
now wait a minute. The steel, Jake. Go back to the steel. The steel stayed bent.
Oh, yeah.
The steel has stayed bent, so that's
cool.
obviously it's failed in a sense. The bending strength from that test, anyway.
And then the pine wood...
This will surprise you.
Oh,
Yeah, it's hardly deflected.
what, 10 mil? Not even that?
I think this is what really surprises people. Timber is a surprisingly resilient and bend resistant material. You can take enormous loads. Of course, with timber though, it gets to a point where it does bend, but then it cracks.
And then
whereas a
breaks.
metal will bend and then stay bent or carry on bending. A plastic tends to, if it's an acrylic, tends to snap because it's brittle. And a styrene there, the softer plastics,
It'll just bend.
will just carry on bending. A spring steel, you can quite bend it quite a lot, put a bit more load, and it will just bend straight back, and that will take quite a lot of load. So
And then,
I suppose the spring steel is a good example of why it is called spring steel, and it's about a 0.1% carbon content in that steel.
and then the balsa wood doesn't
Yeah,
really...
I'm surprised it does balsa wood, because balsa wood's really good for model making, but obviously at this scale it has its limitations.
Yeah.
Anyway, I thought that was quite useful. So that was a summary on the key word there, bending, and we're trying to look at this graph I've done here, okay, and it shows the elastic deformation and then the yield point of when it can't return back to its original shape, and it stretches in the plastic area and then it eventually breaks, okay, which of course we do not want to happen. In fact, we don't want any material really get to what we call the yield point in the green there, okay.
Isn't that when it breaks?
It's the beginning of the end of the material in effect. It's a good point actually. Any other points, Jake?
I don't think so.
No. So this is how all these products over the years, including the aircraft, have been gradually developed so they don't fall out of the sky. Did you enjoy that, Jake?
Yeah.
Well done. Excellent.
Shedhacks.
Shedhacks.